Okay, now in this lecture we will discuss about the vector diagrams and equivalent circuit of both ideal transformer as well as actual transformer. So first, what is this vector diagram? See, we are learning about an AC machine. So whatever quantities we are learning, we have to consider that it will be having both magnitude and direction. That you call it as vector quantities. So basically how this vector quantity is different from scalar quantity. In the scalar quantity, we are considered only about the magnitude, whereas in the case of vector quantities, we have to consider both magnitude as well as direction. Okay. So the first case which we are discussing is about ideal transformer. That is, already I have explained about the assumptions which we use in the case of ideal transformer. That is no resistance, no magnetic leakage, thereby no voltage drop, no power loss, etc., etc. Okay, so first we will see the how this ideal transformer will behave when there is no load connected, that is no load condition. Okay, so here is a circuit diagram. So let us consider an ideal transformer whose secondary side is open and the primary winding is connected to a sinusoidal alternating voltage V1. Okay, so here you can see we are giving an input voltage V1, okay, which is alternating in nature. If the quantity is AC, we will represent it like this. If the quantity is DC, we represent like this. Okay, so we are giving an input voltage V1 to the primary of this transformer, and here you can see the secondary. Secondary is open, which means the current which will be flowing I2 will be equal to 0. Okay, so that makes the condition E2 equal to V2. Okay, there is no voltage drop. So the induced EMF and the voltage, terminal voltage V2 will be the same. Now let's discuss about the current. What about the current? Okay, now here you can see that when you apply an alternating voltage to the primary, definitely there will be a flow of current. What type of current? Alternating current. And here the primary coil, we are considering the primary coil as purely inductive. What is the meaning of that? That is, we assume that there is no resistance for that primary winding only. So that means it is acting as a pure inductive coil. Okay. And what about the current? The primary winding will draw the current Im. Okay, so the primary will be that that is under no load conditions. Usually we indicate the input current as I0. Okay, so I0 means the input current drawn by the transformer under no load condition. Now in the case of ideal transformer under no load condition, this current will be equal to Im. Okay, and this Im is called the magnetizing component of the current because this current is responsible for producing the flux phi. Okay, oh, so Im is a magnetizing component of the current which will produce the flux. So for an ideal transformer under no load condition, the input current I0 is equal to Im. Okay, now we will see how this current and voltage, what will be the phasor difference between this current and voltage. Now here you are saying that this is a purely inductive load. Okay, so in the case of inductive load, if the voltage is given as like this, voltage is V1, then what about the current flowing through the inductor? It will be lagging by an angle 90 degree. So this is 90 degree and this will be I0. So it is lagging behind the voltage. Or you can see that the current is following the voltage. That is, if the voltage is rotating like this, after 90 degrees, the current will start rotating. Or there is always a phase difference of 90 degrees between voltage and current in the case of purely inductive load. Okay, now let's analyze this further. Okay, now as we have learned before, we can take the flux expression for the flux as phi is equal to phi m into sine omega t. When already we saw this, the derivation of the induced EMF. Here you can see that both E1 as well as E2, it is lagging behind the flux by 90 degrees. Suppose if I am drawing a flux phi like this, Then what about the vectors of induced EMF E1 and E2 based on this equation? It will be like this because they are lagging the flux by 90 degrees. So I can take it as E2 and this will be E1. See, E1 and E2 both are induced EMF and both are lagging behind the flux by 90 degrees. Okay, fine. Okay, now let's think about the applied voltage V1. So in the input we are giving V1, as I told before, based on the working principle of transformer. When you give an input voltage V1, there will be an induced EMF E1 in the primary, right? These two will oppose each other. So actually you can take right V1 is equal to minus E1. So if you know the direction of E1, then what will be the direction of V1? It will be just opposite to it, right? So here we know the direction of E1. So V1 will be like this. So V1 is just opposite to E1. That is why we write it V1 is equal to minus E1. Okay. And this is actually the vector diagram. This is what I explained here. That is, you have the flux here. Okay. And this flux is produced by which current? Magnetizing component of the current Im. That is, you can write I0. That is, under no load condition, for an ideal transformer, the input current is given by I0, which is equal to Im. And this is the component which will produce the flux. Both are in phase. Okay. That is, if we draw flux like this, current also will be like this. Both are in the same line, which means there is no phase difference. So already I explained about E1, E2, which will be lagging behind the flux by 90 degrees. Okay, and also V1. V1 will be just opposite to E1. And here you can see another expression which I have written, that is E2 is equal to V2. What is the reason for that? Because this is an ideal transformer, so there is no voltage drop. So if there is no voltage drop, whatever EMF is induced in the secondary, it will be available to the load. Okay, hope this is clear. Now let's see the graphical representation of this waveforms. Okay, first I will show you the flux. See, this is the flux. See the waveform of the flux? It is an alternating quantity. That is why it has got both positive as well as negative cycle. And next I will show you the current Im. This is a current which is producing the flux. So it will be the same along the, so it is in phase with the flux. See, both are becoming 0 at this point. Okay, maximum at the same point, again becoming 0 like this. Okay, now next we will see what about the induced EMF waveform. So you know both E1 and E2 are lagging behind the flux by 90 degree. So if the flux is starting from this particular point, from where EMF will start E1 will start from this point. Okay, so the phase difference between these 2 points is 90 degree, which means after 90, that is after this flux starts, after 90 degrees only the EMF will be induced. That is, the phase difference of 90 degrees is there between the flux and the induced EMF. So you can draw like this. This is E1. This is a positive cycle and this is a negative cycle. Fine. Okay. Next, what about the induced EMF in the secondary, that is E2? Suppose if you think that this is a step-up transformer. So for a step-up transformer, E2 will be greater than E1, right? That is why here you can see the magnitude is higher. But it is also starting at the same point from here, because both are lagging behind the flux by 90 degrees. Okay. So E1 and E2 both are lagging behind the flux by 90 degrees. But E2, the magnitude of E2 is greater than E1 since it is a step-up transformer. Now let's see what about the other one, that is the V1. What about V1? I told you V1 is equal to minus E1, right? So that means it will be just opposite to the waveform of E1, right? So that is why it is coming like this. See here, it is just opposite to E1. Okay. Now let's see the vector diagram of an actual transformer. Okay. So in the case of ideal transformer, there are several assumptions which we have made. That is, there is no resistance, no voltage drop, no leakage flux, no core loss, etc. But definitely when you are giving an input supply to a transformer, there will be something called core loss. So in the transformer, there are mainly two types of losses. One you call it as core loss, that is core loss. Another name for core loss is iron loss. So core loss or iron loss. And this can be classified into two types, hysteresis loss and eddy current loss. Okay, so this is the first loss, and the second loss is copper loss. Copper loss. This copper loss also you can call it as heat loss or I squared R loss, because it is due to the resistance. Okay, so in the case of actual transformer, when you consider the no load, the input power or input supply, it has to contribute to what? It has to supply the hysteresis and eddy current losses that is occurring in the core, and also secondary is open, so you don't have to worry about the voltage drop in the secondary because there is no current, but there will be a small amount of copper loss in the primary winding. So these two losses has to be considered, which means under no load conditions for an actual transformer, the input current I0, it will not be equal to just Im. Okay, it will consist of one more component. We will see what is that component. See, here you can see that. If you see here, you can see the current I0 here. Okay, and now I0, it is a vector, so all the vector quantities has got both magnitude as well as direction. So you have to write I0, you put a dash here, that means it is a vector. If you want, you can put an arrow also. This I0 is equal to Im. Im plus there is another component called IE. What is Im? Im is a magnetizing component of the current which is responsible for producing the flux. And what is IE? IE is the component of the current which will contribute to the core losses as well as a small copper loss in the primary winding. Okay, so now let me take one angle, that is I0. What is the angle between the input current and the input voltage? So actually this is the angle, this one, this is the angle. The angle between I0 and V1, that is input current and input voltage, you take it as phi 0. Phi 0. Okay, now here you can see that this phi 0, that is the angle between, what is the angle? This angle is between the input voltage V1 and the input current I0. So this angle you can see here, it is less than 90 degrees. It is less than 90 degrees. Okay, now let's look at the diagram which we discussed before. In the case of ideal transformer, just see what is the angle between the input current and the input voltage. See here, it is exactly 90 degrees, right? So here phi 0 is 90 degrees. Phi 0 is the angle between the input voltage and the input current. So here it is 90 degrees. It is in the case of ideal transformer. Whereas when we consider the case of actual transformer, here you can see that this phi 0, that is the angle between the input voltage and the input current, phi 0 is less than 90 degrees. Okay, that is very important. Now we can find the components, that is Im and IE, in terms of I0 and phi 0. So you will get Im is equal to I0 sine phi 0, and what about IE? IE is equal to I0 cos phi 0. Okay, so let me write the relation. Im is equal to I0 into sine phi 0 and IE is equal to I0 cos phi 0. So now you can just square the terms and equate it. So sine squared plus cos squared theta, you know it is 1. This squared plus this squared is 1. So you will get I0 squared is equal to Im squared plus IE squared, or finally the expression what you can write is this one. That is IE is equal to, that is this is the component of the current which contributes to the iron loss. Okay, in addition to small loss, copper loss in the primary winding. So that is given by I0 cos phi 0. Then the magnetizing component of the current, which is responsible for producing the flux, is given by Im is equal to I0 sin phi 0. So from that you will get the expression for I0. And also the angle you can find, you have to take tan phi 0. Tan phi 0 is equal to, from here you can write tan phi 0 means opposite side by adjacent side. So you will get tan phi 0 is equal to tan phi 0 is equal to Im by IE. So from that you can find phi 0, that is tan inverse Im by IE. So this is how you find the values of the different components of the current. So when you are asked to explain the vector diagram of an actual transformer or no load condition, you have to explain all these points. That is what is the expression for the flux, that is phi is equal to phi m sin omega t. Then you have to say that second point is both E1 and E2 lag behind this flux by 90 degrees. That is a second point. Third point is the V1 opposes the induced EMF E1. That is why the vector V1 is drawn opposite to E1. That you have to explain. Then you have to write that since this is a no load condition, we can take E2 is equal to V2 because there is no voltage drop. That you have to explain. Then you have to say that the current I0, it consists of two components, IE and IM. IM is a magnetizing component which produces the flux, and IE is a core loss component. Then you have to explain about the phase angle phi 0. That is the phi 0, which is angle between the input voltage V1 and the input current I0 is less than 90. This many points you have to explain after drawing the vector diagram. Then only you will get full marks for that. Okay. Now based on this, let's draw the equivalent circuit of an actual transformer under no load conditions. So here you can see the input voltage V1, the current is I0. It has two components, IE and IM. Okay. E1 is the induced EMF in the primary, E2 is the induced EMF in the secondary. Secondary is open, which means there will not be any current here. So here this I2 will be equal to 0. And V2 is the voltage across the secondary. Okay. So this is the equivalent circuit. Now here this Im means it is a current which produces the flux. So in order to indicate that, we will assume that this current is flowing through an inductor X0. Similarly, this IE is the current which is responsible for the loss, core loss and the small copper loss in the primary winding. So since this is a loss, you represent it like this current flowing through a resistor. So when current flowing through the resistor means it will contribute to the power loss. Okay, that is why it is represented like this. Okay, similarly when you consider the actual this is under no load condition. Okay, similarly when you consider the actual transformer under loaded condition, you have to consider the resistance and the reactance of this winding as well as this winding. Okay. So you can see that in the case of under no load condition, when you discuss about or when you consider the actual transformer, what is the difference when compared with that of the ideal transformer? That is, you are introducing R0 and X0 in parallel with the primary. Okay. Okay, now again there are some few equations, that is, how can you find the expression for the core loss component IE and magnetizing component IM? Okay, so if you see this diagram, you can see that the voltage V1, it is applied to these two resistor as well as the inductor. That is, it is connected in parallel, right? So how can you find IE? IE will be equal to this particular voltage V1 divided by R0, V by I. Similarly, what will be Im? Magnetizing current will be equal to the voltage V1 by X0 because the voltage V1 is appearing across both resistor R0 as well as the inductor X0. So you can easily find the value of IE and Im. Okay. Now this equation is very important. That is, what is the expression for the power input under no load condition? So the power is VI, right? But here, as I told in one of the previous sessions, in the case of transformer, the equation for the power is given by the no load condition. Okay, P0 is equal to the input voltage V1 into current under no load conditions into cos phi 0. This is the expression. Okay, so this is under no load condition. So under no load condition, a very important thing is that if for an actual transformer that is connected under no load condition, the input power which you are giving it will be used for supplying the core loss plus copper loss. This is also very important. Core loss plus copper loss. Okay. Now this is the expression for the core loss or iron loss. You can take it as IE squared R0 or V1 squared by R0. This is another expression. That is, loss is always I squared R or V squared by R. That is power loss. Power, what is the equation for power? VI. You can take it as either I squared R or V squared by R. Now this is a small tutorial problem based on this type. We'll just go through this. A single phase transformer 3300/220 volt, which means V1 is 3300 and V2 is 220 volt, and the frequency is also given 50 Hertz. It takes a no load current of 0.8 amperes. That means I0 is given. I0 is 0.8 amperes. And 500 watt. That means power is also given. Okay. Calculate the active and magnetizing current. So you have to find IM, IE and power factor. What is power factor? Cos phi is called the power factor. Cos phi is called the power factor. Okay, now let's try to do this problem. So the power under no load conditions, I told you input power will be used for supplying the core losses per copper loss. Here we are considering only the core loss. So what is expression? V1 I0 cos phi 0 is equal to 500. Okay. Now I0 is given and you know V1 also. So from that you can find cos phi 0. Okay. So once you find cos phi 0, here actually there is no need for that. You can find I0 cos phi 0 from this expression. See here, you can find I0 cos phi 0. What is I0 cos phi 0? That will be equal to 500 by V1. V1 is given. What is V1? 3300. So you can find expression for the value of I0 cos phi 0, which you will get it as 500 by 3300. That is equal to 0.152 amperes. So this is actually IE, the core loss component. Now I0 is given, right? So very easily you can find IM. Square root of I0 squared minus IE squared. Then you will get this value. The next you are asked to find the value of power factor. So from this expression you can get cos phi 0, that is a power factor, is equal to 500 divided by input voltage, that is 3300 into 3300 into 0.8. From this you will get the value of the power factor. Okay, this is how you do this problem. Okay. Okay, so you will get the power factor as 0.1894. Now let's move on to the next condition, because now we are going to discuss about ideal transformer on loaded condition. So already we discussed about no load condition. Next is loaded condition. So what will happen when a transformer is loaded? Okay. So again this is the circuit diagram of the transformer. Here V1 is the input voltage. I1 is the input current. See here, now the current is not I0, it is taken as I1. That I will explain. Then N1 is the number of turns. N2 is the number of turns in the secondary. I2. See here, now there is a current flow through the load. That current you take it as I2. So I2 is no longer 0. It is having a value. Okay. And also you can see the flux which is linking both the primary and the secondary winding. Now what will be the effect when the transformer is loaded? That is, when the current starts flowing through the load, what will happen? Now the very important thing about this transformer is that the current which is flowing through the load I2, it will depend on the load, type of the load. Okay, so that first we will see that. That is what is written here. That is, the magnitude and direction of the secondary current I2 with respect to the terminal voltage V2 will depend on the load. So there are three types of load. One is a non-inductive load. Non-inductive load means same as resistive load. Resistive load. Okay. The second type of load you call it as inductive load. That is something like you are connecting a coil. And the third one is a capacitive load. That is a capacitor. So based on the type of the load, the current will change, or current will be having the phase of the current with the voltage, that will be different. So that we will see how it is. Okay, if you see, first we will consider a non-inductive load, resistive load. In the case of a resistive load, if the voltage vector, if you are drawing like this, the current vector will be like this. They are in phase. There is no phase difference. Okay. Whereas in the case of an inductive load, if this is the voltage, what will be the current? Current will be 90 degrees lagging. What is the meaning of lagging? Current is following the voltage, or current is behind the voltage. First voltage will go, that is, it is a circulatory motion, right? So the first voltage vector will move, then the current will move, or current will follow the voltage at an angle 90. Now when you consider a capacitive load, suppose if this is a voltage, then current will be something like this. That is, current is leading. First current will flow, and then first current will move, then voltage will move. That is, the rotation is taken in this direction. So first current will be moving, then after that voltage will be moving. So voltage is following the current in the case of capacitive load. So this is very important. Okay. Now we will see what will happen when the current transformer is loaded. So when a transformer is loaded, a current I2 will flow through the secondary. That is the first thing. Of course, a current flowing means it will produce a flux phi2. This is an alternating flux. What this flux will do? This flux, you can call it as secondary flux phi2. And this flux, it will oppose the main flux phi, which is set by the exciting current I0. So if there is a flux phi2 which opposes the main flux, so what will happen? It will weaken the main flux, that is, flux will reduce. So you know the induced EMF, it is proportional to this change in the flux, right? So when the flux is reducing means induced EMF will also try to get reduced, right? So the difference V1 minus E, it will increase. So what is the step? First phi2, there is a flux phi2 due to the flow of the current I2. That is the first step. Phi2 due to the flow of current I2. Next step, phi2 is opposing the main flux. It is opposing the main flux, which means the flux will reduce. So flux reduces, EMF reduces, E1 will reduce. Now when E1 is reducing, V1 is constant, V1 will not change. So when the E1 is reducing, what will be V1 minus E1? It will increase. That means the transformer current I1 will increase. So the transformer will take an additional component of current to handle the counterbalance effect of this I2. Okay, that we will see. That is I1, that is the current taken by the transformer I1, it will not be equal to I0. Okay, it will be equal to I0 plus I1 dash. So what is this I1 dash? I1 dash is nothing, it is a current which will be just equivalent opposite to I2. I1 dash will be equal in magnitude and opposite in direction to I2. I2 is a current which is flowing through the load. Basically, this current will flow opposite to I2, thereby cancelling the effect of I2. Okay. So the current which is drawn by the transformer on loaded condition is given by I1. And what is I0? I0 consists of two. That is, one is the core loss component IE and the other one is a magnetizing component IM. So these are all vectors. So you have to put it something like this. Vector means it is having both direction and magnitude. You cannot just add it. By using vector, addition has to be used. Okay. So finally what we get is the total primary current I1 will be the phasor sum of I1 dash and no load current I0. Okay. So the thing is that when there is a current flow through the load, it will create a flux which opposes the main flux, thereby reducing the EMF. Okay, so when the EMF is reduced, the difference between the input voltage and the EMF will increase, thereby increasing the input current. That is, the transformer will draw more current. One is I0 and the other one is I1 dash. I1 dash is exactly equal in magnitude and opposite to I2, thereby cancelling the effect of the flux phi2. Okay, this is same like what we have discussed in the case of motor also. Okay. sorry, not motor, that is armature reaction. When we discussed about armature reaction, it is basically the reduction in the flux, right? So that counteracting flux, it has to, how will you manage that in order to reduce the effect of armature reaction? You will connect another winding in series with the armature, and you will allow one current to flow opposite in direction. Okay, so that already we have discussed. Okay. So you can see that the flux phi2 which is produced by the secondary MMF N2I2, it will be neutralized. So the effect of flux phi2 which is created by the current flowing through the load will be cancelled by the current I1 dash. Okay. So this is, you can compare this with the armature reaction in the case of generator as well as the motor. Both the generator as well as a motor, this armature reaction is same, like the same concept. Now we will see the vector diagrams of ideal, we are discussing about the ideal transformers, okay, that under loaded condition. Okay, so since there is a loaded condition, the first change, what will be the first change? There will be a current I2, right? Okay, now just we will go through the phasor diagram. First, we will consider a non-inductive load or a resistive load. Okay, so first we will see the current I2. Since this is a resistive load, here you can see V2. Here V2 is equal to E2 because this is an ideal transformer. There is no voltage drop. Now since this is, that is the first point. First point, V2 is equal to, because when you draw the vector diagram, you have to give clear explanation. So the first point is V2 is equal to E2 because this is an ideal transformer and there is no voltage drop. The second point is V2 and I2 are in phase, that they are coming in the one straight line, right? That is, suppose if I am drawing V2 like this, I2 will be like this. They are in phase because this is a resistive load. Now here you can see opposite to I2, exactly opposite to I2. You can see this red color. That is, I am drawing I1 dash. Okay. Now what is the input current of the transformer I1? It is a vector sum of two currents, that is I0 and I1 dash. This I0, of course, it consists of two components, that is IM and IE. Normally it will not be shown. Okay, so you can write I1, the input current of the transformer I1 is equal to I0 plus I1 dash. I0 plus I1 dash. Now the other points are the same which I have mentioned before, that is V1 will be equal to minus E1, that is exactly opposite to E1. And you can see E1 and E2 lagging behind the flux by 90 degrees, as already I have explained. And then what about flux, that is the phase angle phi 1. Phi 1 is angle between the input current I1 and the input voltage V1. Okay, so phi 1 is angle between input voltage V1 and input current I1. And you can see this phi 1 is less than 90. This many details you have to write while explaining about the vector diagram of ideal transformer on no load condition for a resistive load. Now let's look at an inductive load. What is the difference in the case of inductive load? See here. Now V2 is here. You can see V2 here. What about I2? See here I2. I2 is lagging by an angle phi 2. So this is the difference in the case of an inductive load. All other things are same. That is, flux is there, E1 and E2 lagging behind the flux by 90 degrees. Okay. Then you can see V2 is equal to E2 because this is an ideal transformer. Then you can say I2 lagging behind V2 by phi 2. Okay. Then you are drawing I1 exactly opposite to I2. See here, exactly opposite to I2. I am drawing I1 dash. Okay. Then the vector sum of I0 and I1 dash will give what? It will give the input current I1. Okay. So here also I1 is equal to I1 dash plus I0. And what is phi 1? Phi 1 is, this is phi 1. Phi 1 is the angle between I1 and this is phi 1 dash, this is phi 1. See here, this is phi 1. Phi 1 is the angle between the quantities, that is the input current of the transformer and the input voltage. Okay, there also you can see the angle, it is not 90 degrees. So this is about the inductive load in the case of a ideal transformer. Now let's look at the phasor diagram of an ideal transformer on a capacitive load. Capacitive load, I told you, the current will be leading the voltage. So here you can see the vector of V2. V2 is equal to E2 because there is no voltage drop in the case of ideal transformer. Again, E1, E2 lagging behind the flux by 90 degrees. Now here you can see that the current I2 is leading the voltage. That is, current is going first. And what is angle? Phi 2. Right? Now just opposite to I2, I will draw I1 dash because I1 dash will flow equal in magnitude and opposite in direction to I2, and it will cancel the effect of I2. Now the vector sum of I1 dash and I0 will give the input current I1. Okay. Now what is phi 1? Phi 1 is actually, or you can take it as the angle between I1 and V1. Okay. So the angle between I1 and V1, we will take it as phi 1. Okay. So that is about the capacitive load. Now let us consider now the actual transformer on loaded condition. So what will be the difference in the case of actual transformer? See, in the case of ideal transformer, we assume that there is no leakage flux, but actually there will be some flux leakage. So how will you represent that? See, if there is flux, there will be induced EMF. That means an EMF will be induced due to this leakage flux. So how you can represent it is using, I will show you how. This is what? That is the flux phi 1. That is, the entire flux will not be, entire flux produced by the primary winding will not be linking with the secondary winding. Some leakage will be there. So in order to represent that, we will assume that there is an inductor having an inductance L1, so the reactance X1. We will assume that a current is flowing through this inductor. So the product of I1 and X1 will give the induced EMF, E1. Similarly, in the secondary winding also, we will assume that it is having a reactance of X2 and a current I2 is flowing through it. So the product of this I2 and X2 will give the induced EMF E2. That is, this is the induced EMF due to the leakage flux. So how will you represent it? How you will represent it? See here. In the primary, I am adding an inductor to represent the leakage flux. That is, a current I1 is flowing through this inductor, which will induce an EMF given by X1 into L1. Okay. Similarly, in the secondary also, I have introduced an inductor having reactance X2. Okay. So the current flowing through this inductor is I2. Now the product of I2 and X2 will give the induced EMF. So basically, the effect of leakage flux is indicated by introducing a new component, that is an inductor, in both the primary as well as the secondary. So what about R1? R1 indicates the resistance of the primary winding. R2 indicates the resistance of the secondary winding. Now Z1 will be R1 plus JX1. Z1 is equal to R1 plus JX1. So what will be Z2? Z2 will be equal to R2 plus JX2. So this is a secondary impedance. Z2 is a secondary impedance and Z1 is the primary impedance. Okay. So that is how we will introduce the effect of the leakage flux. Okay. So basically this is what I told you. That is X1 into I1. That is equal to the induced EMF. And the expression for the induced EMF is this one. Okay. Now let's see the vector diagram. Before moving on to the vector diagram, now one more thing, there will be change in one more thing. That is, in the case of ideal transformer, we took V2 is equal to E2, right? And V1 is equal to E1. But now in the case of actual transformer, it is not correct. Because when we are giving an input voltage V1, this V1 minus some drop will be there. That is I1 R1 and I1 X1. So V1 minus I1 R1 minus I1 X1 will be equal to E1, right? Similarly here E2 will not be equal to V2. There is some voltage drop. Which are the voltage drop? That is E2 minus I2 R2. This is a voltage drop in the resistance. Again minus This is the reactance drop. This is a voltage drop across the inductor. Okay, that is I2 into X2. So you have to subtract both voltage drops, that is I2 R2 and I2 X2 from E2, then only you will get V2. So this can be represented using two equations. This is the equation. That is the input voltage V1 minus E1 is equal to, or you can say that the input voltage V1 minus this much drop. V1 minus this much drop will be equal to E1, but you write it as minus E1 because I told you this E1 is usually, E1 and V1 are represented opposite to each other. Okay, that is why we are representing it as minus E1. Then what is I1 R1 plus JX1? It is equal to I1 Z1. So I told you Z1 is equal to R1 plus JX1. Similarly, when you consider the secondary, E2 will not be equal to V2. That is E2 minus this many losses will be equal to V2. That is E2 minus I2 R2 minus J I2 XT will be equal to V2. Okay, so you can write E2 is equal to V2 plus I2 Z2. So what is Z2? Z2 is equal to R2 plus J Z2. So these two equations are very important. It is not very difficult. It is very simple. Input voltage V1 minus voltage drop will be equal to minus E1. Similarly, the induced EMF in the secondary E2 minus the voltage drop will be equal to the terminal voltage V2. So based on these two equations, we can draw the vector diagrams for an actual transformer on loaded condition. So this is the diagram. So we will go through this diagram. So first we will consider a resistive load. So as usual, I have represented the flux phi m. Okay. And what about E1 and E2? Here we have the E2. So it is lagging by 90 degrees. Okay. And here we have E1. So see here, now I have represented E1 in the other side. That is why I am writing it as minus E1. Okay. Then here we are considering a resistive load. So that means, suppose if this is the voltage vector V2, you can see the current vector here. Both are in the same line, which means they are in phase. Okay. Now I have V2, I have E2. Here I have V2, here I have E2. Both are not same. So based on this expression here, you can see the expression. How can you get E2 from V2? So you know the point where it is V2. This is V2, this point. So how will you get that? You have to add I2 R2 and J I2 X2. So to the vector V2, and now I'm going to add I2 R2 and J I2 X2. So how will you add this I2 R2? I2 R2 is a voltage drop across a resistor, right? So I'm going to draw a line parallel to I2. See, this is the line parallel to I2. Here you can see. So now I got the drop I2 R2, right? So this is the vector I2 and this is the vector V2, and from vector V2 I am drawing a line parallel to I2, that is equal to I2 R2. Now next I have to add the drop J into I2 X2. So J is a rotating vector of 90 degrees, which means now I will be drawing a line perpendicular to I2. See here, this line. This is perpendicular to I2. So this is the drop I2 X2. Okay, so I added these two to V2. So now what I'm getting is E2. Got it? And if I want, I can join something like this line. This will represent I2 R2 plus I2 X2. So I can write it as I2 Z2. I2 Z2. Okay, similarly, we can try it in the primary side also. That is, once I know the direction of I2, I will draw just opposite one vector to I2. This will be I1 dash. See here, I1 dash. Now I know I0. So the vector sum of I1 dash and I0 will give the input current I1. Okay. Now you can see the phi 1 phase difference. So this phi 1 is the angle between V1 and I1. So now we will see how to get V1. So E1 you already know, E1 vector. So E1 will be drawn minus E1. See here you can see minus E1. Okay. So minus E1. Actual direction of E1 is how? It is same as E2, right? Actually E1 has to come here because both E1 and E2 are lagging the flux by 90 degrees. But now I am drawing E1. I am taking E1 as minus E1. That is why it is coming here. Okay. Now what I am going to, how can I do? To minus E1, this is the point. Now first I will add I1 R1. That is the voltage drop across a resistor. So I know the direction of I1. What is the direction of current I1? See here. This is the direction of current I1. So now I'm going to draw a line parallel to this here. See? Parallel to I1. So this will represent I1 R1. Now similarly, next I have to add J I1 X1, which means J is a 90 degrees vector, right? So I know the direction of I1. So see, now I'm drawing a line perpendicular to I1. So this will represent I1 X1. So I am adding I1 R1 plus I1 X1. Now I will get V1. Okay, and also here I can draw as before a line which will represent I1 Z1. So this is how you draw the vector diagram for an actual transformer under loaded condition for a resistive load. Basically you have to use these two equations. Next thing is you have to see whether it is a resistive load or inductive load or a capacitive load. Now we will move on to the inductive load. So this is a phasor diagram for an actual transformer for an inductive load. So as usual, phi m, E1 lagging behind, E1 and E2 lagging behind 90 degrees. Okay. Now I am taking E1 to this side, minus E1. Okay. Then what about I2 and V2? So this is an inductive load. So if this vector is I2, this will represent V2 because I2 is lagging behind voltage by an angle phi 2. So first you have to draw this. The previous figure I2 and V2 were in one line, but here you can see I2 is lagging behind V2. The rest is the same. So you know the point of V2. Now to V2 I am adding I2 R2. That is, will be parallel to this I2. Then another one is perpendicular to this one. Something like this. So this is I2 X2. I am drawing this I2 X2 perpendicular to I2. And this point will give E2. And what will be this vector? This vector will be I2 Z2. So I know the direction of I2. Now opposite to I2, I will draw I1 dash. See here, this is I1 dash. Now the vector sum of I1 dash and I0 will give the input current I1. Okay, the rest is the same. Now I am going to start from this equation, this first equation. What is the first equation? V is equal to minus E1 plus I1 R1 plus J I1 X1. So to minus E1, first I am adding the drop I1 R1. That is very simple. Same like I1, same direction. I will draw parallel to that, no perpendicular to that. So this will represent I1 X1. And this point, from this point, I will draw a line to the origin which will give the vector V1. And this can be taken as, because this is a sum of I1 R1 and I1 X1, this vector I can take it as I1 Z1. So this is how I draw the vector diagram for an actual transformer on loaded condition for an inductive load. Now let's move to the capacitive load. Now in the capacitive load you can see the only difference is that, see the current and the voltage. Now the current is leading the voltage. It is moving first. See. Okay, so I2 is here. Now I know the point of V2. From V2 what I will do? First I will draw a line parallel to I2. That is I2 R2. These two are parallel. Then I will draw another vector perpendicular to I2, which I call it as I2 X2. So I2 X2 is the voltage drop across the inductor. Now this particular point I will get E2. So this is the vector corresponding to, from here. This is the vector corresponding to E2. Okay, similarly opposite to I2. This is I2. So opposite to I2 I will draw I1 dash. Here I have I0. Vector sum of the I0 and I1 dash will give I1. See here I1. Now again what I will do, I have to get V1 now, right? So I will start from E1. E1 is drawn opposite to minus E1 is drawn opposite to E1. So I will start from this point. First I will draw a line parallel to I1. Okay, that take it as I1 R1. Then perpendicular to I1, I will take it as I1 X1. Then I will get a point here. I will join it with the origin, that will be V1. And the angle between V1, it is very small here, the angle between V1 and I1 will be the phase angle phi 1. So this is how I draw the vector diagram of an actual transformer. It is not that complicated. You have to use these two equations. First thing you have to understand that the angle between V2 and I2. First you have to think that the angle between V2 and I2 depends on the load. That is very important. You just think how it will be for the resistive load, how for inductive load, how for capacitive load. That is the first thing. Second thing is you have to understand that I1 dash, if you get the direction of I2, draw I1 dash opposite to I2. That is the second thing. Third thing, there is this conception is not valid now. V2 is not equal to E2 and V1 is not, E2 and V1 is not equal to E1. These two conditions are now more valid. So you have to apply the above two equations and based on that you have to draw the vector diagrams. So this is about the vector diagram of ideal transformer and actual transformer. We have discussed two cases, no load condition as well as loaded condition. I hope you got an idea about this vector diagrams, but it will be more clear if you draw it and learn. So you have to draw it maybe 2 or 3 times, then only you will be able to get an idea about this. Okay.